So to start our next lesson, we are going to talk about the difference quotient, which is what we discussed back in lesson 18. And then we're going to also start our formal definition of the derivative and compare the two equations. So we're starting off just with a review. This is a review of what we call the difference quotient. And this derivative, this does give us the derivative, but it gives us the derivative at a point. It's the definition of the derivative at a point. And we could usually call that point x equals c. All right, so this is what we did before. Here's our values, x and f of x, c and f of c. And so what we determined was that we could find the derivative at point C, which was the instantaneous rate of change, or the derivative, by taking the limit as x approaches c of f of x minus f of c over x minus c. And we've done several equations like this, and we've written the equation of the tangent line. So I hope we're getting pretty comfortable with this form of the definition. But remember that that only finds the derivative at that given point. So every time I change the point at which I need to find the equation of the tangent line, I've got to start back over. I've got to do this whole process again. And so there has to be a little bit better way that will work for any point. And so that's where the formal definition of the derivative is going to come in. So in the formal definition of a derivative, we are going to still use two separate points, and we're going to try to bring those points together. It's just that the formula is going to look a little different because we want these points to be two arbitrary points. So we have a point marked here at x, f of x, and then you'll notice that they have this little delta x or change in x marked out. So what we're doing is moving over some amount. And so this new point out here is x plus that change, x plus delta x. So this point would be x plus delta x, comma, f of x plus delta x. All right, so now we have our x and our y, and another x and a y, both arbitrary values, but now we don't have to do the derivative over and over and over again every time we're trying to find a point. We can use this. So our coordinates of Q, what it's asking for here, are x plus delta x, f of x plus delta x. And then the slope of the secant line, the slope of the line between these points, just y minus y over x minus x. So we're going to have f of x plus delta x minus f of x over x minus x plus delta x, y minus y over x minus x. Now in the difference quotient, or the derivative at a point, we just took this point and just kept moving it in closer and closer by taking the limit as that x value approached c. As x approached c, we just brought this x in closer and closer and closer to c. We knew the closer we got, the more accurate the slope would be at that point. But since both of these points are arbitrary, then what we're going to do is just take this delta x, this change in x, and make it as close as we can to 0. So by making this change close to 0, it's going to bring these 2 points close together, and we'll have that slope at a given point, or any arbitrary point. And so whenever you take the equation as delta x approaches 0, you get the derivative. And this would be the formal definition of the derivative, which will work for every x value instead of just one at a time. All right, so on the next page, they have several different derivative notations just so that we are becoming familiar with terminology. So when you see this means take the derivative of f of x, or it is equal to the derivative of the original function f of x. This notation we haven't used much, but it does make sense. It's the derivative of y with respect to x. Now we use that little triangle in front of x and y before to talk about the change in y over change in x, or delta y. This is called a delta in Greek letters. So dy over dx is where that came from, delta y over delta x, derivative of y with respect to x. And we're always taking the derivative with respect to x at this time. Eventually we'll talk about some differences in that, but for now, when we take the derivative, we're taking the derivative of y with respect to x. And then, of course, what we just did today was the formal definition of the derivative. And then don't forget that we also have that definition of the derivative at a given point, which would be the limit as x approaches whatever that point is. Remember, this is only at that point of f of x minus f of c over x minus c. All right, so all of these things mean derivative. If you see this, if you see this formula, if you see these notations, all mean derivative. Also, I realized I just kind of skipped over this, so I want to go back and show you on the other page. The denominator here was x minus x plus delta x, and if I take away the parentheses, then I would have x minus x, which are going to zero out. And I also just realized that this is backwards because that's going to give me a negative delta x, and I did this y value minus this y value. So down here, I should have it in the same order. So let's fix that. All right, so this is x plus delta x minus x. They have to be in the same order. And so then I have x plus delta x minus x. The x's zero out, and all I have left is that delta x. So that's why when we look down here at the formula, there's only a delta x down there. All right, so we are going to use this formal definition to find the derivative of this equation. Now, this derivative is going to be kind of a bulky equation, but remember that in the end, it is helpful because then you can find the derivative at any given point without having to start over every single time. All right, so here we go. To use this formula, we're going to have the function at x plus delta x. So everywhere there's an x, I'm going to put an x plus delta x. So we're going to have x plus delta x squared plus 2 times x plus delta x. And that is this portion right here of that equation. Sorry, can't see again. And so this is this first piece minus f of x, which is this equation. X squared plus 2x is our f of x all over delta x. All right, so now we need to simplify that. So x plus delta x squared, we need to square that. We're going to get x squared plus 2x delta x plus delta x squared. So this squared gives us this right here. Plus, and then I'm going to distribute the 2, so plus 2x plus 2 delta x then minus x squared minus 2x all over delta x. And I forgot to put the limit in front of that, so let's do that. Don't leave that out. The limit as delta x approaches 0. All right, so we're going to try to simplify this, and so I've got an x squared here and a minus x squared down here that zero out. Let's see, I've got a 2x here and a minus 2x here that zero out. And I'm not sure any of the rest of these are the same. I've got 2x delta x and a 2 delta x, but I can't combine those. So I have the limit as delta x approaches 0, that up, of 2x delta x plus delta x squared plus 2 delta x all over delta x. All right, so now I can factor a delta x out of all of that stuff in the numerator. So that would give me 2x plus delta x plus 2 all over delta x. And then these will divide out. And so now I have the limit as delta x approaches 0 of 2x plus delta x plus 2. And I can sub in my delta x because it's no longer in that denominator. And when I put in 0 for delta x, I just get 2x plus 2. So the derivative of this function is 2x plus 2. Now let's think about that in terms of a graph. We know that originally this function was a parabola. Now I have a derivative equation that is a line, so it's 1 degree less. Also, this would give me the derivative at any point, or the slope of the tangent line at any point. So if they wanted me to find the slope at 3, then I just plug in 3. 2 times 3 plus 2, or 6 plus 2 would be 8. At x equals 3, my slope is 8. The slope of the tangent line is 8. Or I could do negative 2, f prime of negative 2. I would have 2 times negative 2 plus 2. So negative 4 plus 2 would be negative 2. At x equals negative 2, my slope of the tangent line is negative 2, or the derivative is negative 2. So now that I have it down to a formula, I can use that formula to find the derivative at any point on the graph.